speaker for today, Yotsu. He will talk on Calderón problems for Schrödinger operators.
Thank you for the kind introduction, and thank you for letting me have the opportunity to speak here. So I would like to sort of start by saying that I'm...
Just before you start, you know that we are very ignorant about Schrödinger operators.
You know that we are very ignorant about
It's okay. I know next to nothing about obstacle problems and free boundary. So the reason why I sort of thought it would be a good idea to give a talk here is because a couple of months ago, Henrik suggested to me a problem, an obstacle problem, which is related to inverse problems, the inverse obstacle problem. And we were interested in discussing this together, and I'm sort of here giving a talk about what inverse problems is in hopes that some of you will give me some ideas on how to solve the problem, the obstacle problem that I'm interested in. Hopefully this is more or less the start of a conversation rather than trying to present to you my results. So just to keep this in mind. So I will start, to make everybody more interested, I will start with the obstacle problem that I'm interested in. All right, so the inverse obstacle problem, which Henrik suggested to me. This is suggested to me by Calderón and Petro. All right, so let omega be a subset of Rn, and psi be a continuous obstacle, and G be a continuous boundary function, where G is greater than or equal to psi at the boundary, and you set the solution to the obstacle problem by UG, by UG psi, to be the infimum over all superharmonic functions, such that U is bounded below by the obstacle, and U at the boundary is greater than the boundary condition. Right? So this is the standard obstacle problem that one considers. And so for this, for each solution, I can define what is called the Dirichlet-Neumann map, right? So I define the Dirichlet-Neumann map for the obstacle problem. So I will call this obstacle problem of the boundary condition. So this is what it does is that it takes the boundary condition G and it maps it to the normal derivative of the solution to the free boundary to the obstacle problem with this boundary condition, right? So this is this is called a Dirichlet-Neumann map, right? Why is it called Dirichlet? Well, it takes the Dirichlet boundary condition and it maps the Neumann, which is the normal derivative, right? And of course, so the natural question that I want to consider is the following: if I have two different obstacles, psi1 and psi2, such that the Dirichlet-Neumann map are identical, does that imply, so this is G for all G, and psi1 on the boundary is equal to psi2 on the boundary, does that imply that they are equal in the interior, right? So this is the typical inverse problem that you want to ask, is that you're given some kind of information about the solutions of these two different equations, the obstacle problem for psi1 and the obstacle problem for psi2. Can you deduce from the information that you're given that the two equations are actually the same?
No.
Well, in this case, yes. So immediately, there is there is obstruction to this, right? If you consider the superharmonic envelope to these guys, right? So let psi hat be the superharmonic envelope of psi, then it's very easy to see that lambda psi is equal to lambda psi hat. Right, so the right problem that you should ask is that, does it imply if psi 1 lambda psi 2, does that imply that there's superharmonic envelope agree? Right, so that's the problem that I want to sort of solve at the end of the day. So now I will just switch to what I know a little bit more, which is the analogous problem in the linear Schrödinger operator case. Okay, so I have definitely. So the inverse problem for linear Schrödinger operator. All right, so let Q be a smooth function in a domain, or in this case, I actually want to deal with Riemannian manifolds, where M, G is Riemannian manifold. And consider the Schrödinger operator defined by Laplace plus Q. All right, so this is the Schrödinger operator. And if you want to solve the boundary value problem, Laplace plus QU is equal to 0, U restricted to the boundary is equal to F, assuming that this problem here is well posed.
Sorry, I didn't follow the last part. Why the obstacle should be side equal?
I'm sorry?
Why the obstacle, two obstacles should be equal inside?
Oh,
Why the last equality you wrote?
So that's the question that I want to. That's what I want to deduce.
No, because I thought maybe your answer was yes, they are. Okay.
No. This is like I said. This is the problem that I want to try to understand. All right. So now I'm just telling you the simpler problem, which is something that's a little bit more well understood, which is the linear Schrödinger operator case. All right, so you assume that this boundary value problem, this linear elliptic boundary value problem is well posed. Then what you can do is define the Dirichlet-Neumann map. Lambda sub q, because it depends on q, which takes the boundary value f and it maps it to the normal derivative of the solution. Right, so again, you're taking Dirichlet data and then you spit out Neumann data. And this problem is actually motivated from electric impedance tomography, where if you have an object and you have a conductivity inside and you want to sort of determine what the conductivity is, you put electric potential along the boundary and then you measure the outward current flux and then you try to determine what the conductivity is. Right, so this is the classical Calderón problem. So this is the Calderón problem. All right, so I will sort of give you an idea of what is known for this problem in various cases. All right, so the question, of course, is if lambda q1 is equal to lambda q2, does this imply that q1 is equal to q2? Right, so let's take the general Riemannian manifold case and the Euclidean case. All right, so and also it turns out that in this problem, dimension plays a role. So there is the n is equal to 2 case and the n is greater than or equal to 3 case. All right, so it turns out that on any Riemann surface, that's on any surface, dimension 2, I can answer this question in the affirmative. All right, so I can show that if the Dirichlet-Neumann map of two different potentials agree, then the potentials are the same.
When you say Riemannian manifold, you mean without boundary?
With boundary. So yeah, because I have a boundary value problem. Right. So and of course, if you can do this for any Riemann surface, you can do this in the Euclidean case. And in the 3-dimension and higher case, the Euclidean problem, when the n is a domain, this is actually a well understood problem, and this was the famous work of Sylvester and Ullmann. And in the Riemannian case, in the geometric case, in higher dimensions, so higher dimension manifolds, the answer turns out to be maybe. All right, so I will sort of go into a little bit of detail of what this maybe means later. Okay, so the next bit of this talk is so that I want to just give a survey, an overview of what all of these sort of results involve. What are the main ideas that are involved in these results? All right, and we will start with the oldest one, which is, and it's probably the sort of the easier one to understand, is the one by Sylvester and Ullmann. All right, and every single one of them starts with what is called a boundary integral identity. And this is true in any dimension and in any kind of geometric set. The boundary integral identity. All right, so let Laplace plus Qj Uj be 0. J is equal to 1, 2. So you have two different solutions to two of the different problems. Then, just by a simple integration by parts, you have that the integral of u2 bar u1 times q1 minus q2 in the interior is equal to the boundary integral of u2 bar lambda q1 minus lambda q2 of u1. Now, why is this identity interesting? Well, it's interesting because on the right-hand side here, we have information that we are given. We are told that lambda q1 is equal to lambda q2. Right, so this is the given information. And on the left-hand side here, we have information that we want to deduce. We want to deduce that q1 minus q2 is equal to 0. Right, so this is the information we want.
Why are you using bars on the
You talk complex?
Yeah. So these are complex solutions.
But why are they complex since this is the real Schrödinger?
Qj may be.
Q may be complex.
Q also complex.
Is this important to be complex?
Yes, it is. So at the end of the day, I have to consider complex solutions.
But the Calderón problem was for reals.
Yes.
Yeah.
Yeah. So Q could be, even if Q is real, I still have to talk about complex
So
solutions.
there is no benefit in assuming Q real and everything real.
No.
Okay.
No, not in this case.
Okay.
So on the right-hand side, I have information that I'm given. In particular, I know that Q1 minus Q2 is equal to 0. So, and this is starting to look already really good, is that I have that this thing that I wanted to use to be 0 is orthogonal to all products of solutions, right? And all I need to do is to somehow prove that the products of solutions form a dense subset of L2. Right? And unfortunately, so since I'm considering solutions to two different equations, despite the fact that they all look like the Laplacian, that there is no general principle that says products of solutions are dense. So I have to sort of go in there by hand and try to construct a dense subset of solution, or dense subset of products, such that so that I can deduce that Q1 minus Q2 is equal to 0. And that is essentially the name of the game here, is that we need to construct a rich enough family of solutions such that their products are dense in whatever space that I want to consider.
Span.
Or the span is dense.
It's a matter of tensor product.
All right, so how does Sylvester and Uman go about doing this? Well, so what they did was they said, well, consider a vector zeta, which is in Cn, such that zeta dot zeta is equal to 0. And this does not mean that zeta is equal to 0. All this means that the real part and the imaginary part of this vector is orthogonal and they're of equal length. Then they made the observation that Laplacian e to the zeta dot x is equal to 0. So e to the zeta dot x is actually harmonic simply by this fact. Well, so they say that, well, now, since this equation that I want to construct solutions for, Laplace plus q, is not so far from just the Laplacian, I expect to have solutions to the Laplace plus q u equal to 0 that looks like this. One plus, well, since this equation is not exactly the Laplacian, I expect to sort of gain a little, I expect to need to make a little error adjustment, plus r, and r is the error. And what r does is that the L2 norm of r actually goes to 0 as the frequency here gets large.
It's a kind of WKB symmetries.
Yeah. Exactly. So this is going to be a WKB type solution, right? Except in WKB, you sort of expand a lot of terms. In this one, you only need one term, but you need to construct exact solutions. WKB gives you approximate solutions, right? And WKB will play a very important role later on when we consider the geometric case.
But this trick is only in the flat case.
In the flat case, yeah. So in later on, when we go to manifold, I need something else, right? I need other ideas. All right. So now they say fix a vector z in Rn and pick zeta in Cn such that zeta minus zeta bar is equal to I z, and zeta goes to, the size of zeta goes to infinity. All right, and I have solutions. U1 is equal to e to the zeta dot x, 1 plus remainder. U2 is equal to e to the minus zeta bar dot x, sum 1 plus remainder. And I simply plug in these types of solutions into my boundary integral identity. And because I have chosen zeta such that zeta minus zeta bar is Ix for a fixed vector z, what I get is integral over Rn e to the I z dot x q1 minus q2 plus little o of 1 over zeta is equal to 0. And I take zeta to the size of zeta to infinity while keeping z fixed. I have that the Fourier transform of q1 minus q2 xz is equal to 0. And now I can arbitrarily take what z is, and I have that q1 minus q2 is equal to 0. So the first idea here is to construct solutions that looks like Fourier transform, right? And that is not surprising to expect to have solutions that look like Fourier transforms. And so unfortunately, one thing that in this case is that in order to choose z this way, choose zeta with this property, the dimension has to be greater than equal to 2. All right, so that was a little Indio. So that's why they can only do this result for the dimension 3 and higher case. All right, so as you asked, what happens? This is only works with a flat case, and when I move on to a manifold, I don't have Fourier transform anymore. So what do I do, right? So this is the more modern technology. This is the following the work of Salo, Dos Santos Ferreira, Kurelev, Lasas, and Dos Santos Ferreira, Salo, Koenig, Salo, and Ullmann, is that on a general surface, so on MG, but you can't just consider any manifold. So you have to assume that your manifold is of a product type. So M is an interval times Cartesian product with a codimension 1 manifold. And this is not just a topological product, but it is also a metric product in the sense that G has to be written, you have to be able to write G as dt squared, which is Euclidean metric, plus some G naught, which is G naught is a metric on M naught. And not only that, the underlying codimension 1 manifold M naught G naught has to be special. And I will say what special means later on. So again, I have that the manifold, the boundary integral identity, u2 bar, u1, q1 minus q2 is equal to 0, and I need to construct a rich subset of solutions such that the product is dense, but now I have to do it on a manifold, and I don't have the tools of Fourier analysis available to me. And what they did was they actually constructed solutions of Laplace g plus q u is equal to 0, such that, well, because you have the product structure on the metric, this could be written as minus dt squared plus Laplace g naught plus q u is equal to 0. And they construct solutions which u is equal to t over h plus 1 lambda t v h of x prime plus rh, where h goes to 0 and rh is again little o
Just
of h.
a question about notation. Do you assume the geometric notation for the Laplacian?
You put minus dt
Laplacian.
Yeah, so this is the geometric Laplacian. So from now on, my Laplacian is minus dx
Yeah,
j.
I guess.
Right, or else I get the wave equation, which is not what I want.
Otherwise, it would have been too easy for you.
Okay.
All right, and x prime is a variable in the underlying manifold. So essentially, what this is you take separation of variable, right? You have this separation for the metric, and therefore you can separate variables in t, which is this, and x prime, which is only corresponds to this Laplacian, and you construct solutions that looks like quasimodes, or looks like WKB expansions, where Laplace g naught of vh of x prime is little o of h. That's my, or little o of h to the power of infinity. And vh is of norm 1. And these guys are called quasimodes, or WKB expansion WKB solutions. So if you plug in these types of equations into this boundary integral identity, then you have that, because I already have a separation of variables, I have that there's an integral in t, and there's an integral in the underlying manifold of e to the I lambda t q1 minus q2. This one on the outside. V of x prime dg naught, or dvg naught squared is equal to 0. All right, so what it turns out is that whenever this is a result in semi-classical analysis, that if you have these quasimodes, which is of norm 1 always, in the limit, they will always converge to a probability measure that is invariant under the flow generated by the geodesics. So as h goes to 0, what I have is that I have the Fourier transform in the t variable of q1 minus q2 integrated against d mu is equal to 0, where d mu is a semi-classical measure associated with the Laplacian. All right, so then what I have is that I have the Fourier transform of this, which is invertible, integrated against all semi-classical measures associated with Laplacian is equal to 0. So now the question is are the space of all semi-classical measures associated with Laplacian dense in the set of all measures, right? And what they answer this question by constructing. So you construct VH of x prime such that they concentrate to be d mu is equal to delta gamma, where gamma are geodesics. All right, so now what I have is that the Fourier transform of Q1 minus Q2 integrated along all geodesics of the underlying manifold is equal to 0. So now I have actually converted my PD problem into a dynamics problem. And I want to see if the geodesics transform is invertible. And it turns out that so we need invertibility of geodesics transforms. On the underlying manifold M naught, G naught, and this is doable, and we can do this, and one can do this. For example, on negatively curved manifolds. For example. All right, so the name of the game now is just to sort of push how far can we invert this geodesic transform sort of outside of negatively curved manifolds. So that's kind of the state of the art at the moment in the dimension 3 and higher case. All right. So we're going to go back down to Riemann surfaces. On surfaces, we can do a lot more. So this is the idea by Buch. The theme is that you start with your boundary integral and U2 bar U1, Q1 minus Q2, and assume that omega is the disk. So again, we need to construct special solutions. Such that they are dense.
Stop.
Hey.
There's a problem with
The lock, you push the
cable.
yeah, people will push that in
The cable.
Yeah.
Yes. No, pull it back.
Pull
it back.
I don't want to force it.
Pull it back. The one.
Now maybe
Yeah,
So when
that's
you
what
believe-
belongs in that
Why don't
trend.
you put down the first blackboard to see what's happening behind?
Shall I call?
Pull the second blackboard. First.
yes. Yeah.
And try to.
Now fine,
Yeah.
Bobby.
Now.
Now
That's
I
okay
see.
now.
Now you want
No, but.
put the how suppose the yeah above the above the border, yeah, suppose something.
Well, don't worry about that for the moment. But now we can.
So maybe I just limit myself to one flat point.
No, it's okay. Yeah, just carefully for the fix.
Thanks.
I see.
Alignment.
This was what
Very strong
we're not the best mathematician.
Let's see. All right, so in the n equal to 2 case, I need to construct enough solutions to Laplace plus QU is equal to 0 such that the product is dense. And this is done because in dimension 2, I can no longer use the Fourier transform methods by Sylvester Ullmann. I need a different idea, and this is Bouking's idea. So he says, well, if phi is equal to, say, z squared, then that's a holomorphic function. And holomorphic functions are certainly harmonic, and it's as h goes to 0. So you expect, again, since Laplace plus QU is equal to 0 is not so far from the solutions, so you expect solutions to Laplace plus QU is equal to 0 that looks like e to the phi over h. So expect solutions u that looks like u is equal to e to the phi over h, 1 plus a remainder, which corrects for the fact that this is not the perfect Laplacian. And of course, and just as before, when the frequency goes to infinity, the error term here vanishes. All right, so you plug in these solutions into the boundary integral identity up there. So what you get is 0 is equal to integral e to the I imaginary part of phi over h q1 minus q2 plus little o of h. All right? So observe here that the imaginary part of phi is explicitly written. This has a critical point at 0. And furthermore, it is non-degenerate. So there's a basic idea in microlocal analysis which says that if you have a phase function and you're integrating against that phase function and you have an oscillation, and as oscillation goes higher and higher, this acts like a delta function at the critical points of the phase, and this is called the stationary phase expansion. So essentially, this part here expands as h q1 minus q2 evaluated at the critical point of the phase, which is 0, plus some little o of h. Well, then all you need to do is divide by h and take h to be equal to 0, then q1 minus q2 is 0 at 0. Well, there's really nothing special about the point at 0. I could I can make a translation on z such that I can have a critical point anywhere in the disk that I like, so that I can conclude that q1 minus q2 is identically equal to 0, just by a simple translation argument. All right, so in dimension 2, at least on the disk, this is actually a pretty simple idea, just the application of stationary phase technique. so I have 5 minutes,
Yeah, 5 to 10 minutes.
5 to
10
10 minutes.
minutes.
So the last thing the last case that I'm going to talk about is the extension of this case to a general Riemann surface. Right, so on general Riemann surface, the theorem is, this is by myself and Guillemot, let M and dm be a border surface, and let gamma be an open subset suppose lambda q1 of f is equal to lambda q2 of f. Now, here I'm actually I'm not measuring the entire Dirsham limit map on the boundary. I'm actually doing a little bit better. I'm actually only measuring it on a very small subset of the boundary. So I'm only taking measurements on a small subset instead of the whole space, whole boundary. And furthermore, I'm only allowing inputs that are supported in that small subset. Then Q1 is equal to Q2. All right, so I'll draw you a picture.
So may I ask a question?
Yes.
Can you say something about U1 and U2? Are they equivalent? I mean, if you have this map, remember they're equivalent for.
Sorry?
My question is, can we say U1 equal to U2?
What is U?
I mean, okay. Main question was for obstacle that we had, two obstacles.
Well, if that I don't know.
But since you don't know about the sign of Q2 minus Q1, it should not help. You want that U1, U2 bar be positive. How could it help?
So of course, in the Schrödinger case, you deduce at the end that Q1 is equal to Q2, and then you can say that all your solutions are the same. But there's no direct way to go from boundary value of solutions to solution itself. That if that's the question that you're asking.
Yeah.
Yeah. So that's that I don't know. All right. So here's the Riemann surface with some genus, and I'm only measuring my Dirsham limit map here, and I'm only inputting Dirichlet data here, and I can conclude that the potentials Q1 is equal to Q2. Right, so the difficulties here.
So you have no assumptions on gamma whatsoever, could be any portion of the boundary?
Any portion.
Must be non-void.
Well, yeah, it has to be open. It has to be open. It also can't be like these
not
weird
only
grapple
open.
sets.
Not only open, but non-void. No, you did not. You did not
Right,
prevent
right,
gamma to
yeah,
be void.
yeah. Of course, I mean, not non-empty.
You have to connect
Non-empty.
it, right?
Non-empty.
Manifold.
Uh,
Separation, two manifold separate.
right, yeah, sure, of course. You know, with all the
Yet it's like a unique continuation problem.
Yeah.
at the end of the day, it's a
Similar,
unique
yeah.
continuation problem, right? But it's kind of a unique continuation inverse problem because I'm no longer trying to uniquely continue my solution, but I'm trying to uniquely continue a coefficient in my equation. So how do I do that from right? But it actually not surprisingly, I guess, it uses the same idea as the unique continuation. It uses something called a Calderón estimate, which was developed, or at least Koenig has had a very good idea of what to do, right? And that's how all these microlocal people started to get into this problem. So the difficulties here is the following: well, first of all, I don't have a full set of data. I only have a partial set of data, and as you said, this is going to use some kind of unique continuation type technique. Right. And two is more of a geometric problem. Is that, well, in the disk case, I constructed a holomorphic function that is called z squared. I can write it down very easily. I can translate it easily. I can place my critical points wherever we want. Well, on a Riemann surface, I don't have the luxury of being able to write things down, right? So how do I construct these holomorphic functions? How to construct Morse holomorphic functions with prescribed boundary, with prescribed critical points. So, just 5 more minutes. Is that okay with you?
Yeah, it's fine.
Okay.
You can take a few more minutes. It's
All right.
we're flexible.
So the first part, so I'm going to talk about the first difficulty, and then we're going to talk about the second difficulty. Is, well, usually in the boundary integral identity, I have u1, u2 bar, u1 minus u2 is equal to the boundary integral of the Gershwin-Gilman map. Well, so usually I have that lambda q1 is equal to lambda q2, and I have that the whole right-hand side vanishes. Right here, I don't. Right, so this is only 0 on a very small subset of the boundary, small open subset of the boundary. It's only 0 in gamma. And so I need to somehow kill this entire thing. Well, the one way to do this is if I construct u1 such that it is 0 on the complement of this. Then integral over n u1 u2 bar u1 minus u2 is equal to 0. So we need solutions for Laplace plus q u is equal to 0. And we not only need solutions that looks like this, of this equation, we need the solution to take a special form. Namely, u has to be some exponential plus a remainder. And furthermore, my solution now needs to have some kind of a boundary condition, right? So when I restricted the boundary, I want it to vanish on a large open subset of it. So this seems to be a little bit contradictory already because, well, if u is something exponential, how do I make it vanish on a part of the boundary, right? So this is actually this really nice idea by Emanuilov, Uman, and Yamamoto. So this is And they did this in the case when n was a disk. Well, they say, just as everything before, you think what happens when you don't have a q. When q is 0, what can I do? Right? So then, if phi is holomorphic, not only is it holomorphic, I want phi restricted to the gamma complement. Well, you know that holomorphic functions can't vanish on the boundary on any open subset, but I can ask it to be purely real, right? I'm allowed to do that. Then, Laplace of e to the phi over h, this is definitely harmonic, but if I take the harmonic conjugate of this guy, that is also a harmonic function. And I subtract the two. I subtract the reflected wave. Well, this is, again, a holomorphic function and anti-holomorphic function. They're both harmonic. And furthermore, because you have this boundary condition, I have that e to the phi over h minus e to the phi bar over h restricted to this part is also equal to 0. So now I have, at least I have a way to construct solutions that looks like this and also vanish on part of the boundary. Right? So I'll just write down the requirements that I have. So I need phi gamma complement to be purely real. And 2, I have that it has prescribed critical points. And 3, I need phi to be a Morse function in order to apply stationary phase. And furthermore, phi has to be, of course, holomorphic. Right? So now we seem to have painted ourselves into a corner because holomorphic functions are very stiff objects, and yet we also require all these conditions on it. It seems like we've painted ourselves into a corner. And it turns out that you can do this I'm running out of time here, so I won't go into the details. But if you consider d bar as if you ask yourself the question, what kind of a boundary condition should I impose on the d bar operator such that this question here is a Fredholm operator, and how do I compute its Fredholm index? And it turns out that there is a sort of a if you use some symplectic geometry theory, you can construct kernels to the d bar operator with the right boundary conditions that you need. And I'm sort of out of time here, and the whole point of this talk was not to talk about my result anyways. So I will end here.
Questions?
In the last explanation, you consider harmonic functions, and harmonic functions form an algebra. And it seems that you use the fact that we have an algebra. For instance, when you take the exponential of a harmonic function, you still have a harmonic function. When you rescale by 1/h, you still have an harmonic function. Now, if you deal with a manifold, then your operator is the Laplace-Beltrami operator, and the harmonic functions associated with this operator do not form an algebra. So you cannot take the exponential of a harmonic.
Harmonic functions are never algebra. Holomorphic are.
Okay, holomorphic, I mean.
Yeah.
But do you have an analog of holomorphic functions on a manifold?
Yeah. So it just behaves exactly the same way as on a complex manifold. Anything with a holomorphic.
Complex manifold.
Yeah. So for example, any Riemann surface is a complex manifold, and I have a holomorphic structure on it.
By Riemann surface, you mean?
Any surface is any orientable surface any orientable two-dimensional surface is a Riemann surface.
But for a very special metric.
Yes, but and then with that metric,
so you assume that there is an underlying complex structure on the manifold.
Well, it turns out that whenever you're given a metric, you have a complex structure that's immediately comes from that metric.
If the manifold is if a dimension of a manifold is odd, for instance.
Right. But I'm only thinking the dimension 2 case,
Okay.
of course. And in that case, the Hodge star operator, it gives you a harmonic holomorphic structure which is compatible with the metric. So there's always an underlying holomorphic structure there, of course. That's compatible with the metric. So that my holomorphic functions are harmonic, or else they won't be, right?
Okay.
Or else holomorphic, there's one thing holomorphic is another thing harmonic.
I have a question. So it seems that all these approaches start out with a boundary identity. So for going back to the original problem, you started off from the obstacle one. Do you think there's any hope to reproduce a boundary identity?
I've tried and it's not clear how this is done. Right. So in that sense, I'm a little bit. That's where I'm stuck.
Okay.
Right. I don't have that first step that I need. And in some sense, the boundary integral identity is not a very deep thing. All you need to do is integrate by parts to get it. It's just the Green's formula.
Right.
But then, when you have a nonlinear problem, it doesn't really work very well with these integration by parts techniques.
Other questions or comments? Let's thank the speaker again.